Hello, my dear students. Uh, this lecture is in continuation with the previous lecture I make. Uh, we are going to discuss the dynamic model of DC motor. So, this is dynamic modeling of separately excited DC motor. Okay. Okay. So, uh, what we discussed in previous lecture, we discussed the block diagram of closed loop speed control of this motor. So exactly what we did, let us take a review of that. So what we did, we compared the speed of your DC motor with a reference speed which we need to control. So the error signal was then conditioned through API controller. This generated the armature current reference signal. So our this armature current reference signal depends upon the speed error. We compare this with the measured value of the uh, armature current of the DC motor, which is again conditioned through API controller and then sent to a driver. So the role of driver is to generate necessary pulses for the DC to DC chopper. This DC chopper is externally excited, so this is your chopper, and what this chopper does, it supplies the necessary VA across our DC motor. So this is your armature resistance, this is your field winding. So what we are doing, we are just controlling the duty ratio of this chopper to control the VA, the armature voltage across DC motor, where the VA is related to duty ratio of the chopper and the VS supply. So D is variable, so VA is also variable, and we know that our omega is what? The rotor speed. our omega, the rotor speed of this DC motor, this depends upon omega is equal to that is VA minus IA RA upon K. K is the machine constant. And so this VA can be controlled by varying this duty ratio. And how this duty ratio will change? This ratio will change uh, as per the error signal, the controlled error signal received by the driver EC. Okay, so what we are going to do, we are going to sense this speed, and then sorry, so we are controlling this omega speed, and then through a filter sorry, we are writing this as to be NR. To be omega, so we should remove here. This will be your omega. Okay, now this filter is giving a feedback to the reference signal. So and this IA, before discussing this IA, this complete is the outer speed control of your DC motor control logic. This the error with the speed error will be conditioned through a PI controller. This will generate a armature reference signal, which will be compared with the armature current of this DC motor. So we need to give the feedback here as well. So let us say this will again pass through a filter. Okay, so this is your inner current control. So exactly we know the control logic of controlling the speed of this DC motor. So we know the mathematical model of this PI, how this PI can be written as. This PI may be written as Kp plus Ki upon S. S because this is an integral constant. So this is Kp plus Kis, and this is for speed. So Kps and Is. Okay. Similar expression will also be valid for this PI controller, the current controller. Here it will be Kpc plus Kpic divided by S. Then this driver can generate instantly. The duty ratio will be selected instantly, and this will go to this chopper. This chopper could be represented by some, let us say, K constant. K let us say Kc, we have written, okay, Kc, the chopper constant, divided by 1 plus S T by 2. Okay, where T is the switching frequency of this chopper. So after this, the chopper will generate a VA at a particular D. This VA will actuate this DC motor. So in whole exercise, we just do not know this part. The mathematical model of this part. So it is necessary to derive the mathematical modeling or the mathematical equations that will govern the speed of your DC motor. So let us do that exercise. So basically there are two equations that needed to be uh, uh, known. Actually there are three equations. They are categorized among two equations. One is electrical dynamics, and second is mechanical dynamics. So let us first write down the electrical dynamics. Electrical dynamics depends upon the circuit diagram of your DC motor. So let us draw the circuit diagram. Circuit diagram, you all know you all know it is very familiar with you. There is we can represent one armature resistance, then one inductance. This is the armature of the DC motor with a field winding. Okay, this is so a field current is flowing. Here we supply the armature voltage to this DC motor. This is armature resistance and the leakage inductance. So what we need to do, we just need to write the KVL. Okay, in KVL, one more thing you need to find. This is EB. EB is what? EB is the back EMF induced across the armature winding. That will oppose this. Oppose this EB will is in opposite polarity to your VA. So VA is here. This VA will generate a current. So there will be a drop across RA. So this is plus minus, and there will be plus minus here. So if we write the KVL equation for this, so we can write uh, min, uh, minus VA plus IARA plus L DIA by dt and plus EB is equal to 0. So rearranging the equation, it will be VA is equal to IARA plus L DIA by dt plus EB. Okay, let us take the Laplace transform of this equation, and all the state variables will be converted in S domain. So whatever variables are changing in time, that will be converted to S domain. Like here, what thing could change? VA is a variable. VA changes as per time, as per dt ratio. IA changes as per dt ratio. RA is a constant. LA is a constant, and EB is also a variable. So we will make the conversion. So let us do that. So it will be VA in S domain, that will be RA into IA S domain, plus the integral will be converted to this differential equation can be converted to Laplace like this: LS IAS and plus EBS. So from here, this is the First, dynamic equation. First, electrical dynamic equation. So this will be first. Okay, this could be rearranged, so we can find IA. So IAS will be equal to VAS minus EBS divided by RA plus SLA. So again, we can rearrange this in time constant form. So we can write in here IAS is equal to VA minus EB all in S domain. So this will be equal to that will be 1 upon RA. So this will be 1 plus SLA by RA. So we can write this as to be IAS is equal to VAS minus EBS 1 by RA divided by 1 plus STA, where TA is the time constant of this armature circuit. So let us discuss why we are converting or this equation to this form. Exactly what this represent? This represent a decaying function. If you take the Laplace inverse of this, so what it will become? It will become a decaying function. What does this mean? This means that a function that is decaying with time. Okay, so as per definition of time constant, when let us say this is a p variable, let us say this is IA, the armature current. So this armature current will be having a initial value at t is equal to 0, this point. Now this armature current is decaying as per t. So at t is equal to Ta, the time constant, the current remaining in the circuit is just 37% of the initial value, that is Ia 0. So if we take Ia as to be 1 ampere, let us say that this is 1 ampere, then the value of this point will be just 0.37 ampere. Okay, so this is representing a time constant. Time constant is when the value of a variable that decays to its 37% of the initial value, that is called the time constant of that variable. So we will represent all the variables in the present circuit in terms of time constant, that how fast they are changing, how fast they are decreasing. Okay, so this is the TA is the armature circuit time constant. The current in the armature circuit is decaying as per TA. Now this is your first equation. Okay, the second equation is the torque equation. Torque, how we can write the torque? The torque of your DC motor will depend upon the machine constant K and the current. So torque will be depending upon K, machine constant, and the current, armature current. And you know that armature current depends upon VA. So here we can uh, write the block diagram of the armature circuit. So how can we write down? Just see that. So here it is your VA that has been supplied by your chopper. Then this VA will be VA minus EB, the remaining voltage, which you can see here, VA minus EB. This will, if this is multiplied through this gain, what that will give? This will give current, IA current. So if this multiplied by this gain, what is that gain? That gain is 1 by RA upon 1 plus STA. So what this will be? This will be IAS. Okay, this is VAS, this is EBS. Okay, so this IAS, if multiplied by your machine constant, what this will give? This will give your electromagnetic torque. Okay, so we will complete this thing, but let us complete. So to complete this, we need the mechanical governing equation, because your electromagnetic torque by the motor has been derived through VA and EB. Now this motor torque be uh, will be uh, will be compared to the load torque, which will give your motor through mechanical dynamic equation. So now let us just see what is mechanical dynamic equation. So here it is electrical dynamics. Now let us just derive the mechanical dynamics. So here it is, mechanical dynamic equation. So what does the mechanical dynamic equation tells? It just tells that how the mechanical component, like the rotor of DC motor, is changing. So it changes as per the torque applied. So here the whatever torque is generated by motor, it will be is equal to the load torque plus J d omega by dt. It is the rate of change of DC motor plus B into omega, and plus there is also a variable called C, which do not depends upon omega. But here what we are going to do, we are going to neglect this C part as to be very low. And in the Guru Kumar sir's lecture, in the NPTEL lecture, this B omega has also been neglected, if you will see. But in the lecture class, this we have considered this equation for mechanical dynamics. So I was little confused that how to proceed, because you are studying in at one hand the Guru Kumar sir's video lecture, and second you are having the lecture content which were in the class. So let me tell you that there is no there is no significant difference in both the equations. uh, you can just go through both equations and just see that there is very minute difference is there. So in this PPT, let me take the this b omega. Okay, so so taking the Laplace transform of this, so the variables are here te, tl, omega. These are variable and the constant are j and b. So your this time domain thing which are variable, that will be converted in s domain. So we can take tes, tls plus j. There is a differential, so s will come omega s plus b omega s. Okay, from here we can derive for omega s. What will be omega s? It will be tes minus tls into 1 upon j 1 plus s t m. You can see it is very much similar to the electrical dynamic equation which we have derived. So here what is this tm? Here the tm is your j by b, and what was your ta? Ta was equal to uh, ra by sorry la by ra. Let me tell you that this tm is this tm it ranges in seconds. So let us say 1.5 second. The usual values are in seconds, and this ta values are in milliseconds. There are some 1 millisecond, you can say. So there is a quite a gap. So what this tm is representing, this is the representing how the rotor speed is decaying, how the rotor speed is changing. And what is this ta? Ta is representing how the armature current is changing. So let us just see the difference. Just see. So if we make a single diagram in which t is there, and we make ia, and let us draw the current ia as to be in red, and your omega in black. So if we write here, let us say this is 0.1 second, and this is 0.2, so one will come nearly here. So 1 second. Okay, so your armature current, let us say these are in pu and same value they have. So when we draw ia, it is in milliseconds, so it is the 100 part of 0.01. so it will decay like this. Sorry, so it is going to decay like this. Okay, whereas the omega is having a time constant of 1.5 second, so it will decay like this. So when omega is changing, the armature current has already died out. So you can see that while the omega is changing, there is no effect of ia. The ia effect was only at the millisecond level here, but omega is continuously decreasing. Okay, so there is no significant effect of this change in current at omega. at change in omega. Okay, so let us go back onto our block diagram model. We will take this equation as to be the second equation. So this is your second equation. Or let me take is to be third equation, because our second equation was your torque equation. Let me see where it is. So this is your torque equation. So this is your second equation. Okay, now let us just take the mechanical part. You can see. So let us uh, let us just T is here, so we need to subtract TLS and put this gain out in here to get your omega. So let us do that. So this has to be TL will be subtracted, then the gain will be there. So gain will be, how much is gain? 1 upon B divided by 1 plus STM. So what this will give? This will give your omega S. Okay, so this omega when multiplied by the machine constant, this will give your EB. Okay, now we can just write the transfer function. Omega S upon VS. How we can write? This will be GS, the open loop gain, 1 plus HS into GS. So this is a typical control equation in which GS is the open loop gain. So when there is no feedback, then this is GS. So our GS is this thing, and our HS is this thing. So let us take TLS to be 0. So at TL is equal to 0, what will be this equation? This will be GS is 1 upon RA upon 1 plus STA into K into 1 by B divided by 1 plus STM, and this will be divided by 1 plus the H is K here, to K into GS. So GS is this part, so we can write K square BRA upon 1 plus STA, sorry, so this could be converted to K by BRA divided by 1 plus STA 1 plus STM plus K square by BI. Okay, now just see that there are two equations which are multiplied. 1 plus STA is multiplied to 1 plus STM. So here we can see this transfer function. The omega is depending your this is what this is equal to omega upon VAS. So when you are giving some VA, like some VA is given, then omega will start changing as per your this transform this gain. Your omega will change. So let me just write it down because it will be more clear. So your omega s is equal to this transfer function into your VAS. So whenever your VA is changing, whenever this VA you are changing, this omega will change as per your transfer function. Okay, so it is like this TF is multiplied to this VAS, and this TF is what? This TF is this thing. So just see what is this TF. This is K upon B RA 1 plus STA into 1 plus STM plus this constant. This value K is constant, B constant, RA is constant. Now just see these two things are multiplied. This is 1 plus STA, this is 1 plus STM. So TA is in millisecond range and TM is in seconds range. So if you multiply these two, what will happen? So so it means this omega is depending upon this time constant of this armature circuit, the electrical time constant, and also the mechanical time constant. So your electrical time constant is changing very fast. The TA is very low. So we can always neglect this 1 plus STA with respect to this 1 plus STA. Okay. So this is exactly the transfer function equation. This is the mathematical modeling of your DC motor. Now this whole block diagram could be represented by a single value, that will be if you give your VA, if you give your VA, if you change your VA, this VA will change as per the transfer function and will give you omega. So by this we are able to just find the missing link. So we have started from this block diagram. We have started from this, sorry, this block diagram. In this the mathematical relation, this relation we were not knowing. Okay, the relation between VA and omega. Now we also know this part. So a complete mathematical equation, uh, this closed loop is defined uh, through another mathematical equation. Now we can just optimize these two PI controller. So uh, the final part of this whole exercise will be to design your PI controllers. So we will design your our current controller, we will design our speed controller such that uh, uh, a specific performance uh, index of DC motor meets. So I will upload another lecture. For time being, you can go through the second NPTEL lecture, which I have the link I have shared in the in the Google Classroom, in which you can find a PPT, which has all the links of the NPTEL lecture by Guru Kumar sir. So you can just go through with the second lecture which is there. uh, so okay, thank you for now. All the best. Okay.